All right, welcome to PyCSE again. Today we're going to follow up on the video I did yesterday on statistics and talk about how do we tell if two measurements are really different or not. So what's the issue at hand? Yesterday you saw that if we just take 3 samples or a small number of samples of a normal distribution, then the average of those are normally distributed. So let's refresh our memories from scipy.stats import norm, and we'll use numpy and matplotlib a couple of times today too. So what we did yesterday was look at making random samples. Let's say we want just 3, and the location of these is by default at 0, that's the mean, and the scale is 1. That's the standard deviation, and we can put in a size here, and if I say that this is equal to 3, then this will give me 3 random numbers, and you can tell already the average of these will be negative. But if you do it a bunch of times, sometimes you'll get a positive, sometimes you'll get a negative, and you can see that you might fall into a trap of wondering which one is right. Of course, they're all right. You only get the right kind of mean of 0 in the limit of a very large number. But suppose you have made a set of 3 measurements and another person made a set of 3 measurements, and you're trying to decide, are they different or not? How do we even think about doing this? So what we're going to do is use Python and SciPy to simulate this and get a lot of measurements. All right, so I'm going to use some shorthand here that we went over in a lot of detail yesterday. So let's say I'm going to make 100,000 measurements, and each one has three measurements in it. And so this will generate that array, and now we're just going to average, and we'll go along axis equals 1, and let's look at m1.shape. This should be 100,000 elements that are the average of 3 measurements. Okay, so that's my measurements. Now let's just do it again, and this will be a second set of measurements. Now, one thing that we might want to or we often do while doing statistics is we make an assumption or hypothesis. So let's assume that these measurements are drawn from the same distribution where we know the standard deviation is 1, and then we don't exactly know what the average is. If we did, we would be measuring it. But let's assume that they're the same. And now let's take a look at a histogram of M1 minus M2. So let's call that D M1 minus M2, and we'll look at the histogram, and then let's say that the density is true so that it's normalized, and then bins equal 100 because we have a lot of data points. And let's have a look at what this is. So this looks like a normal distribution, and in fact we can show that it is. So let's say x equals np.linspace. This goes from, let's say, -4 to 4. And then let's make a plot on top of it, plot.plot x, and then norm.pdf. What we need to do is fit it, so we're going to evaluate this at x, and then I'm going to use this shorthand, norm.fit d. Right, so norm.fit_d will give me the mean and the standard deviation. The star here will unpack it into those 2 arguments, and this should then put a line over this, and you can see that it looks quite good here as a fit. All right, so let's take a look. What are those properties of D? That has a standard deviation that is close to 0 and a mean that's close to 0 and a standard deviation of about 0.815. Now, where does the 0.815 come from? We had a standard deviation of 1 in the system that we are sampling from, and the difference of those 2 means has a standard deviation that's less than 1. So it turns out that this is the square root of 2/3. and the 2 or the 3 is the number of samples that we took, and this is really the square root of 1/3 plus 1/3. So in general, the standard deviation of the mean of that difference is going to be the standard deviation or the variance square, standard deviation squared, or the variance of the first distribution divided by the number of samples, and the second distribution divided by the number of samples. And here it's 1 for both of them and 3 for both of them. So we end up with that. Okay, so back to the question at hand. How do we use this information to tell if two differences are important or not? You can see that from this distribution, if each of us only takes 3 measurements, we expect, like almost all the time, that the difference will be between plus or minus 3. So it's pretty easy to see here that if you saw a difference of 4, that the odds of it being part of this distribution, which requires the two means to be the same, is very, very small. So if somebody made a measurement and said the average is 0, and another person said the average is 4, you could be fairly confident just looking at this that it's not likely that you would have gotten a value of 4 if the two means are the same. And in statistics speak, that means you reject that original hypothesis and conclude that they're different. But what about a difference of 1, right? There is some probability that it's 1 or minus 1. And so we could go back and ask, what's the probability of getting a difference of, say, plus or minus 1? Well, we get that from the CDF. So we can take the CDF of this distribution and calculate the CDF of 1 and subtract the CDF of minus 1, and that would tell you what fraction of those points fall in that range. So let's just try it. All right, so we need, let's go ahead and save these parameters. And let's write norm.cdf. Let's look at the syntax of this. We need x and then the location and the scale. Okay, so the CDF up to 1 star p minus norm.cdf minus 1 star p. This will give us the area under the curve between plus or minus 1, and it's about 78%. So if you got anything that fell between 1 and minus 1 in this case, 78% of the samples fall in that range. You couldn't be very confident that that the means were actually different, right? And if we make this to be plus or minus 2, then we get 98%. So any difference that falls within plus or minus 2 is likely to mean that the means are probably the same. That is a little more than, let's round up, 99% of the observations fall between plus or minus 2 here. And so if you get anything in the plus or minus 2 range, you probably shouldn't be too confident that the means are actually different, just that you got a particular sample that happened to have that difference. Now you might recall that there is a norm PPF, and we can say norm.ppf, and let's say we want 97.5. This will give us something that's more explicit. So if you want the 95% confidence interval of what that mean as you expect, it's going to be about plus or minus 1.59 in this case. And if I recall, there is actually a interval that we could use. And then we just have to figure out what the alpha is. I believe it's, let's try 0.95 star p. That should give us the plus or minus minus 1.59, minus 1.6. That's interesting that it's not symmetric. I thought it probably ought to have been. Always a surprise. Okay, so basically if you make a measurement and someone else makes a measurement and it is greater than 1.6, then you could be 95% confident that they're different. And if it's less than that, then you should conclude that probably they are the same. All right, that is the kind of fast, quick, and dirty way of looking at this. Obviously, if you use more and more data points, then your confidence in these means gets better and better. So let's just see. Let's go up here. Here, if we increase this to be 30. Let's print norm.fit_d. Then let's go back to 3 and just double check how this is. So with 3 measurements, the standard deviation is 0.8. If you make 30, it's 0.25. And if you make 300, then it takes a little bit longer to calculate, but it's 0.08. So then anytime you have something that is bigger than about 2 of these, so 0.16, then you would conclude that they're actually different compared to 30, where it's about 0.5, and at 3, that difference is about 2 times 0.8, which is about 1.6. And that is practically what we've seen down here. Okay, so what we illustrated today is a statistical framework to think about, are 2 measurements different, based on what you expect from the infinite distribution, the normal distribution, where you know what the standard deviation that you're sampling from is. That's pretty important. It turns out if you don't know the standard deviation and you have to estimate that from your data too, instead of just the mean, then you don't have a normal distribution. It falls under something that looks more like the student t distribution. It's a similar idea, just a different distribution to do the evaluation from. So that's how we use Python and SciPy to do statistical analysis and build up some intuition about what these things mean. Thanks for coming, and see you next time.